Welcome to our bonus module, Introduction to PADIM. The content you will see here was recorded live in Singapore at a recent Fieldcom Group Working Group meeting. This module provides a high-level introduction to the concepts of PADIM. The PADIM Specification Project Group is continually improving and expanding the specifications to cover additional applications and device types. This presentation and demonstration of the technology will be focusing on HART devices. While adding PADIM to existing instrumentation is a new feature, this is not yet required for registration. After watching the walkthrough, we encourage you to take a look at the sample source code. If you have any questions about PADIM and are interested in incorporating it into your future FTI package, please reach out to us after the course. We are pleased to have special guest speakers joining us today to provide an overview of PADIM in the following agenda topics. Frank Fengler, Head of Cybersecurity and Connectivity at ABB, will introduce PADIM and its application in NOAA use cases. Paul Sirico, Marketing Director at Fieldcom Group, will demonstrate a system using PADIM technology. Bob Weinberger, Design Engineer at Emerson Automation Solutions, will discuss the requirements for EDD developers to implement PADIM. Lastly, Andreas Esemann, Project Leader at Vega, will explore a sample HART EDD implementing PADIM mapping and demonstrate how it looks in the reference runtime and an OPC UA client. If you have not yet downloaded the sample zip file, please feel free to pause the video and do that now. This will allow you to follow along with Andreas later. With that, let's begin our introduction to PADIM.
PADIM, what is it? And you see this nice picture here. We will come back to it. First, to specify it, I have a slide created with a goal, and let's just read it very carefully. The goal is to replicate a field device in hosts, cloud, and analytic application in a common information model, inclusive of user core parameter to maximize the value of data from field devices of all types, brands, and protocols. That's our goal. What do we need to reach it? And in order to achieve it, we need all organizations serving the process industry with both hosts and devices to agree upon the critical parameters and create a standard of such parameters that are machine readable with common nomenclature, maximize interoperability with OPC UA device specification and FDI, which are built upon the same standard information model for devices specification by OPCF, OPC Foundation. Solution, PADIM was created in alignment with Namur, OPC Foundation, Fieldcom Group, and PI over 3 years to develop a specification that identifies common parameters covering primary field devices, develop a machine-readable binary for each parameter, and use unified semantic standardized data definition, provide process to expand to additional devices such as what we are doing now, process analyzers, and other assets critical to process automation products and use cases. So this just as a summary. So if you look to it there, we tried to really write it down on one slide, on the first slide. So now going a little bit deeper. So the challenge is data is not quickly accessible or understandable, and it's distributed across many devices and facilities. And like you can see in the picture there, you have many systems, protocols, versions of tools, people in the data chain, which you have to handle. And each tool and device and protocol has a unique access and presentation of data. So that's really the challenge what we have. And we translate PADIM with IT-friendly device data. We started with a NOAA, with a Namur together, with a NOAA information model, Namur Open Architecture, and are reusing also data which is defined in common data dictionaries, the IEC Common Data Dictionary, and explore also collaboration with other standardization bodies. The other point we decided is to use the OPC UA data model specification and to standardize on OPC UA the parameter. We have developed a model to support vendors including parameters which are not standardized, so vendor-specific parameter or proprietary parameter. And we are considering developing mapping tools for other common protocols. Coming back to the picture on the introduction, so we have connection to cloud application, analytical application or engines, mobile devices, and of course host systems. We see it as IIoT device integration through alignment, also with next gen FLC initiative, and compatible also with other ongoing open architecture initiative like OPAF, designed to be usable by using PA industry. So process automation is our target industry, and also of course certification and registration is important for us. To recall the use cases where we started, that was not 19. That is a long time ago. But in principle, there have not too many things changed from the use case perspective, but you would like to have more data in monitoring and application or monitoring and optimization application to be used. And we started 2017. And health monitoring and diagnostic is, I would say, the number one use case. Backup is an important topic, also looking to cybersecurity, device dimensioning. It's always the question, okay, is my device oversized? Can I reduce something? Can I save costs through it? Unique identification. From a cybersecurity perspective, also the number one use case, because I need to know with whom I'm speaking. And this is not on a human perspective, but also for devices. Automated as built, of course. What I have planned is that's what I'm using finally. And as we are not have just instruments like 1993 or so, we have now multivariable devices. So devices can have more than one variable. So the question is, read this multivariable process values. Therefore, we have there also two use cases, and the one also what possibility check means, what devices, what values can be read out. So that are the NOAA use cases, the NE 176, where they are described. This is a nice slide showing the steps which we have. So today we are here still in step one. We are with the existing installed base and are thinking heavily, okay, how can we make access to this data? What can we do? We have protocols, HART, Profibus FF installed. And what we can do today is to have kind of edge devices using OPC UA, using PADIM, and using FDI to get this data out of the installed base. And there we will learn more today in this workshop. The second step is then using already Ethernet APL with OPC UA as a second channel. and still using for control the normal, let's say, protocols, Profinet, Ethernet IP, whatever. The third step, I would say, is then if we just use the OPC UA as a protocol based on Ethernet APL, and not just for monitoring and optimization, but also for the control, so that there is one protocol. Common to all of these steps is PADIM, the information model where we're starting now and which goes through all the steps as shown here. Now we have also another nice picture. It's, I think also we have it in principle for several years. The question is how to extend an automation system with PADIM. What are the technical solutions? It explains FDI, and what we see here very nice is all these different communication protocols, then having communication server, the OPC UA as a common interface into the FDI server. And this FDI server, you can, let's say, put in an FDI package explaining or defining what the device can offer, and which is extended with an OPC UA interface where you can connect an FDI client or on top an OPC UA client. With the FDI client, of course, you are using the UI to view the parameter, to view what is in the instrument. And by adding the PADIM functionality to the FDI server, you have a machine-readable interface and can connect an OPC UA client to make use of this data and use it in cloud application. So that's a picture which summarizes it. And let's go to next slide. So that we get a protocol-independent device information model. So we have FDI as one technology which we can use, and bring it together with PADIM provides us machine-readable information. And of course, there's always the question, how do I get information out of the devices? Do I need mapping, or can I directly use a PADIM parameter? And I distinguish always a little bit between PADIM parameter and PADIM, including the OPC UA. So the PADIM parameter as such have all an ERD for the Common Data Dictionary, which is a definition. So I know exactly what that parameter means. And by having this ERD together with the value of the parameter, I know what I can do in any cloud application with this parameter. Therefore, if I have this PADIM parameter directly in the device, that makes my life very easy. I have not to map or to think about how I bring this together. So if the device can provide this PADIM parameter idly, including the definition from the IEC, then I do not do further mapping and can directly use it. But of course, the communication protocol, I need to get it out of the device by using the communication protocol. This is a slide which also summarizes the PADIM architecture. We have a manufacturer independent information model to exchange data in a common format, and using the unified semantic data, the IEC 61987 from Data Dictionary. We have a structure. We are using OPC UA, parts of it, the identification interface, for example, device health interface. But then we have also a number of signals inside the device, and where we can have in one device more than one signal, so a multivariable device. What is also important, and I would like to mention, is the identification link string. This is you know perhaps a small QR code, which is also on the device, which you could scan and get the, I call it the standardized serial number of the device. That is also part within the information model PADIM and in the parameter product instance URI, and which you can read out. And this is also part of the digital certificate called IDEF ID. So there it's important, like I said, identification is an important use case also for cybersecurity, so to identify this device. Semantic. So often people asking, what is semantic? What is it now? We have already a lot of things, but what we are trying to do is to more standardize also the semantic in a way that we can really distinguish. If I say there's a jaguar, then it depends also where I'm standing. So I'm in the forest, I'm in a city. The jaguar, the speed is 50 kilometers per hour or something like that. Then you can also not see what I'm talking about. And therefore, it's important to provide also the context, what I mean. So are we talking about a car or are we talking about a cat? That is semantic, what we mean. And I tried to put also a picture with our process industry. So we could, for example, have two devices installed in a plant, both measuring the same value, mass flow in this example. But now if something is failing, then it's also the questions, what are you measuring? And there the ERD, which is shown here on the slide, tells you what it is. For example, ABB 290 stands then for mass flow rate. It's the same with both. But at the end, if I would like to know what is the device, then I have here ABA 763 for the Coriolis mass flow meter, or there for the differential pressure transmitter, the ABA 767. And the other use case which we had at the beginning, okay, what else could you measure? Then it replies also with the ERD telling you, okay, these are the other measurements I could provide. We have PADIM 1.0, and this was mainly focusing on instrumentation, pressure, differential pressure, temperature, flow, level, positioner for identification, diagnosis, process variables, and core parameter. It implements the Namur open architecture, the NE176, and we standardized approximately 50 parameters, started 2017 and 2020 we finished. Now just finished the 1.1. Where we added the analyzers, mainly for monitoring and optimization application in the first phase, TOC, CGA, and pH. And there will be also a next phase. And this one we started in 2020 and are now in the starting phase of balloting. This slide just gives an impression about the analyzers. So on the left-hand side, we are looking to the analyzer as the device having parameters there. On the right-hand side, we have the different signals an analyzer could have. So analyzer, you see it, there are a lot of possibilities. Therefore, it's even more parameters than for instruments. Another very important topic where we spend a lot of time is profiles and facets. So how can you test it? And there is a, I would say, nice concept within OPC UA where you have so-called conformance units. That's the begin where it starts. You build a conformance unit for a lot of things. And then you bring this conformance units together in profiles and facets. If you ask me, okay, what's the difference with profiles and facets, that becomes sometimes a little bit challenging. But from the viewpoint how we build it is, we are starting always with a profile. This is a PADIM Core 2017 or 2022 server profile. It has a little bit difference in the security. And then we are adding facets to it, depending on, so you have always one of these core profiles, and then you're editing a temperature server facet and a diagnosis facet to build your instrument. So that's from the thinking how it works. Where do I find the specification? We have it on the FCG share file.
SharePoint, yes.
Okay, I have always to think SharePoint or share file. This is on the share file, and where you can download it. There's also an open available version which you can just view on the internet. So without any access rights, that's also possible. Now, what we are doing, we have more owners. We started, as mentioned, mainly with in FCG, in Fieldcom Group, then together with OPCF, getting requirements from Namur, working also close with P&O. We have now even more owners in the boat, let's say. And here's also a diagram how it works. And we have mainly Namur for writing use cases requirements for devices, but they are providing it on the one hand side directly to the PADIM working group, on the other hand side to the satellites, we called it. So the other organization who are looking, okay, what are the use cases, and have then also requirements for asset-specific models to feed in to the PADIM working group. And that is a meeting we have next week to go through it and gather this information. The number of organizations you see in the circle, I don't think I need to name all of them. Thank you.
But I want to kind of set the stage a little bit for y'all. So what's behind me here on this picture? First of all, the two smiling guys are Kurt Pulzer and Bernhard Gut, who work for us as contractors in Germany. Kurt in particular has done a fantastic job of putting together a demo system. This demo system is typically located on a stand-up wall in Karlsruhe, but I couldn't find in my very well organized computer and online storage, I couldn't find any one of the half dozen great pictures of the demo system that are in Karlsruhe. But I was able to find a really good one of this of the demo system that was taken last year at the Hanover Messe conference. And the demo system demonstrates all the Fieldcom group technologies, FDI, wireless HART, etc. And we have instruments from a variety of different manufacturers on it. We have remote I/O, we have cloud gateways, we have a lot of stuff on this, and then we have applications that we can show on it, including many of the major asset management systems. And in this case, we're showing a web app, a PADIM web app from a company named Flowserve, who I'm sure you're all familiar with. They have a product called Red Raven that is part of our demo suite. I won't be showing that today. I will be showing a couple of other things. So if you move to the next slide. So, the way this system, this demo system, is configured to show off PADIM. This is your marketing guy's description of how everything flows. So first of all, you have field instruments with FDI device packages that support PADIM located on the system. I'm highlighting this Flowserve valve positioner right now here, since that's one of the components that is on the Flowserve system. This in turn is a HART instrument. It connects into a HART multiplexer that then eventually will feed into some infrastructure and a remote I/O, and eventually into an edge gateway. Okay, and the edge gateway in this case is running some code writes, cloud server software. The data is then fed into the cloud, okay? And one note here is, the cloud is not a unified entity. There are actually many types of clouds, and and when you're building a product that might be a monitoring optimization application, picking out which cloud you want to use, whether you want to use Azure or AWS, or in our case Cumulocity or something, is one of the big decisions in making a development. But anyway, in this first demo that I want to show you is a demonstration of one of the cloud clients that we've put together that CodeWrights actually helped build or built in for an Akamai demonstration that we did last year. And if this video plays right, you'll see how PADIM information can be transmitted from this device up into the cloud and back down into a web client for viewing various Namur use cases, some of the ones that Frank described in his last presentation.
I will now demonstrate PADIM usage with a cloud application. Here you can see a cloud application that shows the location of the field devices, which are currently in Germany, while I am in the United States. So from here I go to my list of products that are connected and all the devices that are attached. In this case, we have a server created by CodeWrights running on a Phoenix Contact IO, as Arnold shows. Now we can see the network as it was built. And here you see a listing of all the devices with their PADIM information provided. This includes identity information, pictures of the device, information about the setup of the device, the serial number that's found in the housing, as well as values. What you'll notice is there is the tag, there is the address via the hard IP, and also the location of it within the network, because each device is also connected to a hard I/O. Notice that the values have now come in. This is because we're looking at an archive tool. This is not a control system. This is just for asset management. Therefore, the data that is shown for the live updates is only coming in every few minutes. However, data related to health and status of the device is sent on a 3-second update to ensure that any issues in the devices are reported and captured. If we look at the data from the device, we can set up a data historian. We can set up that frequency of updates. As I said, I'm only gathering the data every few minutes, although I'm getting the status every few seconds. In this case, I'm looking at the live values, not archived and not trends, but we could capture trends over time, setting up trend ranges and then date ranges and looking at the history of the device operation. If we take a little deeper dive into the specific device, in this case a 5408, we see that we have the Namur NE107 status showing good, everything's working, and an overview of device information. Currently no alarms, that's why we have a good status from the device, and everything is healthy, functional, and working as we expect. So as we go through each PADIM, we could see these for every device in the network.
So that was an example of a web application that was developed by CodeWrights, and it was developed pretty quickly. It didn't take a whole lot of time because there's toolkits available. There's there's good people that know how to create user interfaces, and a lot of these components these graph components and things are fairly simple and straightforward to use. So what I'm hoping you're getting out of this is that once you have the infrastructure set up and you have the PADIM information model at hand, it's fairly easy to create web apps for particular applications or to address some of these Namur use cases. So let's take now I want to take a look at a more traditional asset management system, which frankly I'm probably a lot less familiar with than many of you here. And the example I want to show here is something kind of related to what Frank was talking about. I think it's in this video. And it's the example of PADIM mapping. So Frank, correct me if I do this wrong. So what you're seeing here in the center column here is the information that might be available in a specific device. What you're seeing here is the information that, on how that information would be assigned to a PA-DIM, I'm just gonna call it an element. I don't know if it's a signal or what, but there's a bunch of terms that I'll probably use incorrectly. So, in some cases, if you're running an asset management system like ABB FIM, which we'll show in the next example, you might want to be able to map a device, a parameter here to another PA-DIM field that just might not be available, or vice versa, or something, or reassign things. So on the next page, the next demo, we've got Sean again, and this time Sean's going to walk through this ABB FIM demo that we also created for Akuma.
Here is a view of the PA-DIM where you can see device health, manufacturer, and model information. Now let's look at it through the ABB Field Information Manager, an actual FDI host. Here you'll see when I open the device, I'm connected to the ABB controller, which is attached to the ABB device. And I have the FDI package for this device loaded. And from this, I can go to the device settings. And from here, you can see all the information that FDI presents. Each of the items that we want to view in the PA-DIM could be mapped to PA-DIM either by the vendor, or we might want to set up a mapping for a device that we already have installed that does not yet have a PA-DIM mapping. So in this case, the ABB tool allows us to map data. What you'll notice is that each item can be mapped to a PA-DIM semantic information. That semantic information is how every device is accessed, regardless of manufacturer or type. So for example, all temperature devices will have a temperature signal type where we can see the signal tag and the units and all the information. In this case, it is a temperature device, so we're providing that temperature via PA-DIM to the cloud model. Here you can see we have range values, we have process values, we also have identity information, and all of this is available through the PA-DIM. We also can use a generic package if we do not have a specific package for that particular device. In this case, the PA-DIM allows us to see the NMOR status as well as the values and the overall health of the device without a specific FDI package for that particular device. In this case, we're also able to view the details of the device because we have the FDI package. We can make calibrations, configurations as a result of that. Once again, we can see that tools outside of the host could have access to the data, as shown in this example. So we have a controller. Now if we go into simulation mode and we want to simulate that maintenance is required, this will cause the PA-DIM reflected in the cloud or remotely to indicate the device needs maintenance. What you'll notice is that because it's a remote tool, not running locally on the system, it does take a moment for it to update. Once it updates, you then know that you need to take action on that particular device. But again, this is global coverage. This is not local. So now there's a remote tool that has captured the status of the device. We now can check in and see the health of the overall global install base of the products.
The conclusion on this section is that, as you can see, we can all, even though PA-DIM is a relatively new technology, a relatively new spec, and the PA-DIM information model server is now been added into 1.6. something or other, and you can all build things. It's fairly easy to get the information that you need out of the device, get it into a web app, get it into an asset management system, get it into a proprietary web app from a member, or a proprietary application from a member, and generate some real value. So we started out this working group on Monday. I said one of the messages that I wanted to put out to members that I'm going to do right here and right now again is it's time to start thinking about building PA-DIM servers and PA-DIM information models for the devices that you have and that are in your development roadmap, because applications like FIM can take advantage of that information right now, and it's hugely beneficial. I think that's all that I have for this section, and the rest of this is on how to go about and build it, right? All right, thank you.
Right, so Frank kind of shared what PADIM is. Paul gave us a good description of what you can do with it and why it's valuable. So what I'll be talking about is if, as we saw, instead of having customers or end users manually map PADIM information in their devices, what's required for developers to have that information already provided in their devices so that people can make use of it, applications can make use of it. So what do we have to do to provide the optimal support for PADIM in our products? Are there device firmware requirements? Are there requirements for what we do in our FDI package, aka the EDD, or anything else? And the good news is not much. There's not a lot that's required of us to get our mapping added into our devices and packages. So if we start with the device firmware side, most firmware, I'm focusing on a heart device here, but other protocols much the same. The field devices already have this information that the PADIM model has standardized. It's already available on the device, so there's nothing you really need to do in firmware to add things like the identification information, what kind of signals your device provides, temperature, pressure, flow, all the different signals, and device health. We all know those are there already. But there are some that aren't necessarily in the field device already to be mapped to. So from a device firmware consideration, it'd be good, best practice, you get the most optimal support if you are building a new device or making a revision to an existing device, to consider including some of the information that PADIM models can map to include that information in the device so that it can be mapped. So I have a few examples there, like a manufacturer URI is something that PADIM has in its model that maybe you don't have a direct way to read out of your device. Condensed status, I kind of have with an asterisk because some of the protocols do have a standardized way, so you may have condensed status already, and that'd be great, so it's already in your device, you can map to it. But the big takeaway is, as you're looking at the PADIM standard and what it has, look at what your device is missing and consider adding it. If we flip to the package side, again, good news. If you already have devices that already have FDI packages, EDDs developed, those same DDs are the foundation for providing mapping. You just have to do a little bit of mapping inside your DD, add it to your existing DD, but the tools you use are the same and the process is the same. So as we said before, if the device is missing some information, and let's say it's not practical to do a firmware update, maybe you're considering providing mapping for existing devices that are already in the field that obviously you're not going to change the firmware for, you can add additional information into the DD itself in some cases. So the manufacturer URI was one that I called out before. If you don't have it in the device, you might be able to create a local variable in the DD that has a default value of whatever your manufacturer URI is. So now the DD instance in your FDI server will have a node that has something that you can map to get your URI without even touching your field device. That's an easy one because it's constant, you just put it in there, but in some other cases, like a product instance URI, where each instance of your device needs to be unique, and you can't just hard code one value, you can even go as far as to having a method in your DD that calculates a value that might satisfy something that the PADIM model is looking for. So again, you can do a change to your DD without your device to get this extra information that can be valuable. So for the things that are in the device already, you just add the mapping in the DD to say, hey, look, this product, this variable that I have in my DD should map to this information node in the PADIM. You specify that with using a mapping construct, and then it's available for applications to use. Okay, what if neither one of these can work? What if you have the example here is software revision. So PADIM has a software revision node. You don't happen to have a command in your device or the data in your device to read it. You can't really put in the package because you don't know which package is going to be talking to a particular device. And so if you could do neither of one of those, it doesn't mean you can't still have mapping in your DD. It just means you skip that one. So certain pieces of data that you just can't get out of the device or create, just skip it. That's pretty easy. So that's it. I mean, those are the kind of the considerations when you're going about providing mapping from PADIM to your device. Just a quick summary recap. You make your firmware follow the protocols the same as you've always done. Nothing new other than if possible, make small modifications to add some of the missing information into your devices if possible. And if you can't do that, add the information into the DD if that's possible. And if you can't do that, leave the rest unmapped. So that's the basics of what you need to do the mappings. We're going to be seeing some examples coming up in the next after break, or where we've created some materials to help you with this mapping, so you don't just have to sit down and figure it out yourself. We'll see a demonstration of actually doing this, adding the mapping into a DD, and showing how it gets realized in a demonstration system.
Welcome to this part of the PADIM workshop, where I will try to explain how an existing FDI package can be extended to the OPC UA mapping to support PADIM information model. So I'm Andreas Esenmann, sitting here in Germany, working for Vega, for all of those who don't know me. So the agenda, I will show all components that are involved, and then we will shortly look what relevant documents exist and where to find this information. Then I will show what the nodeset file is and how you can use a tool to browse the nodeset file. But honestly, all of this is not necessary for you as a DD developer to really create the mapping in the FDI package. Then we will look at the things that have been done by the FCG Standard Hard DD working group, because we prepared some mapping macros which will make the life very easy for the DD developer to integrate the mapping into the FDI package. And in the end of all this, I will give a practical demo with the FDI IDE toolchain just to show how all this fits together. So let's start and look at the components that are involved to create and have this PADIM mapping coming from the FDI package. Of course, first of all, we will have an EDD with a mapping enhancement. This EDD will be tokenized just like all EDDs. And then you have the FDI package. This FDI package will be consumed by the EDD engine, a part of the reference runtime environment. And there's another component, the device model service, which then delivers the information coming from this FDI package to another component, which is called the PADIM server. And all this is part of your FDI host. And this is already implemented for the reference runtime environment. And to this PADIM server, you can connect any OPC UA client to see the information model, the complete node in that namespace. And of course, there are some other interesting parts. There is a so-called PADIM node set, which is a machine-readable file that comes along with a PADIM specification. But that's not necessarily the knowledge of a DD developer to create the mapping, as already mentioned. The documents, important documents that you might want to take a closer look to get a deeper understanding of all of this. So first of all, we have the companion specification PADIM. And this companion specification has some dependencies of namespaces. So this companion specification relies on the IRDI dictionary and the DI and UA information model coming from the OPC Foundation. You can get this companion specification as the FCG document. Here you see the complete naming of that companion specification. And as this document defines the information model, we have a special part of the FDI specification. It's the part 8, this document. And in this part 8, you can see how you can add elements to your EDD to integrate some mapping to any OPC UA mapping, to any OPC UA information model. So this is not specific to PADIM information model, but this explains in detail how you have to enhance your EDD to create this information for an OPC UA information model. And then, of course, because this might be, almost a deep dive, we created an application guide which explains in simple steps what you have to do to enhance your EDD for the PAD mapping. And this is also available on FCG side with this document. And then last but not least, we created a sample, which we will have a look that can be a very good starting point if you want to work on your own DD, because I think every DD developer is happy if he sees an example how it's done. And so that is a good starting point then. Okay, let's have a look at the companion specification. We already saw this picture because I think Frank had it in his presentation already. So this means the PADIM specification defines the information model in general, but there are 3 areas of special interest. One is the information to identify a device, like manufacturer, model, device tag. You can see this like a digital faceplate of the device. And I hope you see my mouse. This is this area for the identification. Then there are the signals of the device. So signals is somehow OPC UA language for a DD developer. This would be the measurement values of the device. So the device variables. This is this area. And then there's a third area which is looking at the device health of the device, where you see the device status in the end. Okay, then let's have a look at the node.z file. I already mentioned that along with any companion specification, there's a machine readable file where all type and object definitions are inside, and this file is called node.z file. In general, it's just an XML file that can be examined by any XML editor. But of course, there are some special node.z file editors, and one is, for example, the Xiome OPC UA modeling editor, and this one you can use to browse through the information model. And so if you want to use this editor, I have here a screenshot. Then you first have to import the information models that are from which the PADIM information model is depending on. I have it here because if we go back, it's depending on the DI node.z and the IRD node.z file. So if you want to use the Xiome, you first have to import these two node.z files before you can import the PADIM node.z file. And then in the end, you see user interface, graphical user interface, where you see the PADIM type with all the elements that we already saw in the specification. So if you see here asset ID, you see asset ID in the specification. But once more, this work is not needed for a DD developer. This is only if you want to get a deeper understanding what is in the PADIM information model. If we want to prepare us for the mapping for PADIM in the FDI package, then there is a perfect starting point. I already mentioned that. If you look at the sample code, the sample PADIM, which will have the PADIM mapping integrated, and this will be part of the next version of the FDI IDE 1.6. So, and with that sample, there are two new helper files, PADIM standard, which is the namespace definition for PADIM, and PADIM macros, which supports or which includes some macros that support the mapping for different signal types. And in your DD, you just have to include those two files and then you're set. Okay, then maybe some general notes how the PADIM type in the FDI package is created, because we use the DD element collection for that. And so if we take a look at that, we have a namespace collection, which is part of this standard include file. So you don't have to write this by your own. You get it for free by including that file. But in this namespace collection, we have identifiers that link to to the different namespaces, so to the UA namespace and to the DI namespace. And if you want to reference one of the DI elements, of course, or for example, manufacturer, then you just have to use this _ DI _ as a prefix of the element. So let's have a look at that. So you have the manufacturer ID, for example, and in the DI, in the DI information model, there's the element manufacturer. And because it's coming from the DI namespace, you have to use this prefix, _ DI _ manufacturer. And for example, in the end, we have the signal set, which is coming from the PADIM. And here we have the prefix _ PADIM _ signal set. You see here, prefix PADIM. What we have to do then is really we have to create this collection for the PADIM type in the FDI package. We already saw this collection, and here you see all attributes that can be mapped, including, so there are some mandatory which should exist, and then there are some optional which might exist. For example, if your device has a display, then you can have the element for the display language, or you have the possibility when did the last change of the configuration happen, something like that. And you even could map the method to reset the device. So your work will be to look which elements are already existing in the device. Bob mentioned this already in his presentation. So the elements you already have in your device, you add just the variable name to the corresponding element. So for example, the manufacturer ID shouldn't be a problem. The device type shouldn't be a problem because each hard device should have this information. But as Bob already mentioned, some information might not exist in the device itself, but can be easily created in the DD itself by using the mechanism of a local DD variable. So you, for example, create a DD variable for the manufacturer URI, and you give the right default value, and then you map this local manufacturer URI to the mandatory element manufacturer URI coming from the DI information model. And that's once more the reason why you see this prefix _ DI _. Another thing is that you can use a method to create or to calculate values that you want to map, and so that the return value of this method then is the value for this element. And one very good example could be if you want to map the product instance URI, which is also a mandatory element. And one thing could be that you do a method that manufacturer URI, something like that. And then you see here, you have this method, product instance URI, which then is mapped here to the product instance URI. So after you created this collection, you have to map this, of course, to the PADIM type. And this is done by the new language element semantic map. And then you just have to give this semantic map a name. Here you see it's called device type map, and it Yeah, the name of the element, in this way, it's coming from OPC UA, PADIM specification, PADIM type, and you use the name of the collection to map it against this element. So here you see collection device type, and it's PADIM type coming from the PADIM specification. And then everything is set. So once more, how is this identifier built? It starts with OPC UA to explain, okay, it's an OPC UA mapping, and then you have again this namespace identifier to PADIM __ PADIM _. Then after we created this collection for the PADIM type, the other area of the three are how to create the signal mapping. And if we look at the specification, then we see that there are a lot of signal types. For example, there is analytical measurement variable type, level measurement, density, pressure, flow, temperature, and so on, and more to come. To be honest, Frank gave us some future topics which will bring additional signal types, of course. And we started creating mapping macros for this set, let me say, of existing signal types. So we support pressure, temperature, level, analytical, totalizers, flow, mass flow, actual volume flow, normalized volume flow, actual density, and control signals. And for each of this, we created a macro set so that it's really easy to create the mapping. And you don't have to know too much on the information model itself. So, for example, if we want to create a level measurement signal, then we use the mapping macro level measurement _ process signal. And if we look at that, don't worry, you don't have to write this by your own, because this is part of one of these header files that we just include, the PADIM macros.h. So, but I just want to explain that there we have the level measurement process signal macro, which we then use as a DD developer in our own DD, and you have to give some arguments. So you have to give a signal name. In this case, you just can use signal. This is used inside these macros as a postfix for several DD items that have to be created by this macro. And then you have a signal label, just to give the signal a label. Then you have to tell the signal tag. So this would be a reference to a DD variable which holds the tag of that signal for your device. And then we have the device variable collection, and you just have to give the index which of the variables is the level signal in this case. And then we have the low and high variables, which gives the range of the signal. In the end, it just looks like this. In your DD, you just use the macro and give the elements, and then you are already set to have this level measurement signal. And but you have to remember that a device can have more than just one signal. So all the signals then together are being collected, and the collection is implemented as a EDD menu. And so we have the signal set, and in the items of this, in this menu, we have to add all the different signals. And the signal set itself then again sits in the PADIM type. Here you see it right here as the signal set. Here we have this menu. The third interesting part is how to create the device health information. And there you can use a DD method to evaluate and create the current NE107 status of the device. So, for example, universal command 48 of a Hard7 device can be a good starting point for that. And the implementation of this method then can use some device-specific information to tell which error bit is in which error class. And you see here, it's the method, a helper method get device health, which can then be implemented. And in this example, we just execute the command 48, and then we say, okay, depending on which bit might be set, we give the several NE107 status information, and then we return it back. So normal failure, check function, out of spec, and maintenance required. This is also part of the sample code, so you can see how this is implemented and copy it and use it for your own DD in the end. So, and then there is one other interesting thing, because some of the signal types need some information of type enumerated. And this one example is the sensor type of a temperature measurement variable type. And how can the different enum values of such an enumeration being mapped to the PADIM information model? For this mapping, we use the multi-state dictionary entry discrete type. And you see here two snippets which show how this is done. So we have the DD variable. Of course, here in the example, it's a local variable. In reality, I think this would be a real device variable, which is of type enumerated and has several numeric values, and then the label or the string value for each of this enumerated value. And because this can be very device dependent, so in one device, the 0 might be a PD100. In a device from another manufacturer, this might be 100 or whatever. So we have to ensure that in the PADIM information model, this 0 gets connected to the IRDI of PD100. And this, again, is done by a semantic map, which by using, as already mentioned, the multi-state dictionary entry discrete type. And then here you see again the 0 from PD100 is mapped to the IRDI for PD100 and the 1 for PD1000. So this is how you can map enumerations to the PADIM information model or to the OPC UA information models in general. So to go online and see the result of the work being done in the package, of course, you first have to create the FDI package with that mapping. Then you have to tokenize this DD, create the FDI package. You have to load. So this is then the tokenizing in the FDI IDE. Then you have to load the package in the reference runtime and go online with the device. This starts up the PADIM server of the reference runtime. And then you can connect an OPC UA client to that server. And in our example, in my example, I will use the UA expert for that. And you can connect then to the PADIM server. And then you can check what you see in this server. And if you then look at the address space, you will see the device that is existing, and then you can compare this to the information model coming from the specification. And of course, there are some things like the manufacturer URI that you see coming in the or being defined in the specification, and all these elements you can then have and browse in this UA expert. Then let me switch to the FDI IDE. And I already mentioned that we created two big helper files, PADIM standard and PADIM macros. And you just have to include them. We can take a look at the PADIM standard because I mentioned that you need namespace collection, but because this namespace collection is the same for all DD developers, we already created this. So you already saw a screenshot of the namespace collection with these prefixes. And then what I didn't show so far is, for example, the UA namespace is really defined, and you have here the URL of that namespace. So this is done, and if you just include this, you don't have to make any changes. And then the other one is the PADIM macros. The PADIM macros is this complete set to support many of the different signal types. So there are a lot of different types that are already supported. And maybe, so here you see level measurement, analytical, actual, and so on, many of them. And what we also already did is because the hard unit codes have to be mapped in a manner like enumerations. So what you here see is all the hard unit codes already mapped to the UNECE information. So some work that already has been done. So if you have some device-specific unit codes, then you might have to make some minor changes. But I think most of us only use the standard hard unit codes, and for that, everything is set. And then going back to the sample, so we include these two files. And then I already mentioned everything for PADIM starts with a PADIM type. And so we create the semantic map for that PADIM type, and we have to create this collection, then really putting all the different things together. So in the sample, you see some local variables that are then later on used in that collection to map some information. So for the manufacturer URI, which then goes to a field com group, we have a method prepared to calculate the product instance URI. Of course, what you would have to do for your real device, you have to replace this by some useful algorithms. One suggestion would be use your manufacturer URI and append somehow the serial number to that. And then we have the method device health, which I already mentioned that in this example, we suggest that you just use command 48 and then use some examination of the results of that command to decide which any 107 status is the right one for your device. Then in this sample, we don't have a real serial number. Maybe it's worth to mention this because there is no universal hard command that you can use today to read out the serial number being on the faceplate of your device. So many of the devices might have some device-specific command to read that serial number. Here it's just simulated by a local DD variable, which is holding some serial number, which, to be honest, is complete nonsense to use a local DD variable for this, because your DD is for your device type, and the serial number should be for each instance of this device type, right? So this is a very bad idea to use a local serial number, a local DD variable for that. But to have a complete sample for this mapping, we just use that way. But you see here, there's to do replace this by a real device variable. The same is if you have a product code, you could use it and read it out of the device, or maybe you have it because this might be something that you can really use or use a local DD variable for. And hardware revision and software revision. Yes, hardware revision might be difficult if you cannot read it out of the device. Local software revision, as you will have different FDI packages for different device revisions, you might help yourself by using a local DD variable, which then returns or has the value in the right format for the PADM information model. So these are all variables that are preparing or to get ready to put them together to this collection of PADM type. And here you just see, okay, we have the different elements coming from the PADM specification, and we map this then to the different device variables, local variables, even methods like here. And already here, but we will see this comes below the signal set holding all the different signals of the device. And in this sample, we have a multi-signal device, so there are a lot of different signals coming below. Creating signals, we have an example for each signal type that is supported in this PADM macros library. And if you want to play around and only have one signal or only having two signals, then you just comment the line out, and then the signal will be gone. In the sample, as we will provide it, all signals will be existing and be alive, so 11 in total. And these different signal types are then part of the signal set, which we saw is a part of the PADIM type. So in the menu signal set, you see, of course, only if this macro exists, you then integrate the different types. This is interesting because the macros create DD elements, and sometimes it might be a challenge to see, because some of the types only create an analog signal variable type, and others have some specialized types. So you can really use this menu signal set to get an idea which type will be created by the, or which DD element will be created by these macros. If you wanna, or if you do not want to study how the macros really work. And then let's have a look how you can, let's say, really implement then one of these signal types. If you, for example, want to create an analytical measurement variable type, you have to use this macro. As I already mentioned, you have to give it an idea, like signal 1 in this case, a label, a tag, then the index to the device variables array. And then in this sample, we use a lower sensor limit and upper sensor limit, but we had a discussion on this, that this is not really perfect, because we should really have the measurement range as the lower and upper limit. So you might want to change this for your real device. And then there are other signal types. For example, if you look here at the totalizer, totalizer has additional elements like the pulse value and the pulse width, which are created in this example as local variables. For a real device, of course, these will come out of the device. And so if you can study the sample, and you will see for all these elements how they have to be implemented. And I think if you look at this, you will have a good idea how to do this for your own DD and your own device. Maybe we look once more for some DD elements which are of element enumerated. Here you see the sensor type of a temperature measurement variable type, because this macro for a temperature measurement process signal needs the sensor type variable. And because your sensor type has your enumerated values, you have to map this to the IRD elements. And in this example, you see how you can do it. So, and if these are the signals, and if this is all set, then as already mentioned, you can use your AND script to tokenize this DD, create the FDI package, as you do it already now without the mapping. So nothing special on this. The tokenizer will tokenize it, and you will have the package created. Then you switch to the reference runtime, where I am connected with a reference runtime to a real device. And let's try and use that element and connect to the server. Here you see the FDI PADIM server is up and running, and we say some security, or we select security and connect to that. Then we are here live, and we can go online with that PADIM server, and in the device set, you then see this device from the PADIM server. And for example, if we go back to the FDI package in the reference runtime, we see here as the measurement loop name some element, and this is mapped in this package as the asset ID. And if we select the asset ID, then the value is read out of the device and is offered in the OPC UA namespace with a correct value, like this, right? And then in this sample device, we have two signals, the level and electronic temperature. And if we go to that signal value, analog signal, then we will hopefully get some value. It's 23 point something. And if we look at the device itself, measured values, then we see the 23. So this is real and live. And if we look at the engineering units, for example, then we see, then we see the unit ID, this IRDI, and as the display name, you see the meter, as we saw it right here, meter. So that's how it works. My main message for all DD developers is, because in the beginning, we might fear that we know all about how to write a DD, and now to create this PADIM mapping, we need to be OPC UA experts. But this is not the case. If you look at the macros being provided, which takes care of most of it, and if you see how easy it is to create just a signal type by using these mapping macros, then I think every DD developer will be ready to integrate this PADIM mapping to the FDI packages.